Welcome to the second module 2 of EEE 2234 Digital Electronics Laboratory. In module 1, we examined some digital logic gates. We examined their truth table, the relationship between their inputs and the output. We examined their characteristics and how they differ from each other. We used the live wire virtual laboratory, and today we will continue in that same vein. So I enjoin you to pay attention to the concepts we would examine today. And so we'll be switching over to the live wire virtual laboratory now. Welcome to another video lecture series using the live wire professional edition once again. So let's continue from where we stopped. Last video lecture series, we are converting base 2 to base 10. We stated last video lecture that all digital information are in base 2. They are either zeros or 1, logic 0 or logic 1. We said that logic 1 in the real life, or in real physical system, represents 5 volts. So binary, when you hear about binary, we're talking about base 2. So let's digital information is in base 2. So digital information is binary in nature, but we can understand it better if we convert base 2 to base 10. Sometimes you can see digital information in base 2 and not really understand what it means. It's useful to convert it to other bases like base 10. Convert it to base 10 can help you, understanding understanding the information better, or it gives you greater insight to what the digital information is if you convert it to other bases. But natively, we work with base 2 in digital systems, logic 0, logic 1. So for example, we can convert 6 in base 10 to base 2. So let's look at how to convert base 2 or base 10 to base 2. For example, we'll be looking at converting 6 from base 10 to base 2. So let's draw a table. If you are doing this, you can basically, of course, use your pen and paper. If we're in class, I'll probably have done this on the board, so it's not compulsory you have to use a table like this. Or you can just draw a mini table with your pen and paper to mimic something like this. So we have 6 and then 2. 6 is the number we want to convert to base 2. So we see here that 2 times 3 gives us 6. 2 times 1 gives us 2, remainder 1. You just long division. You like normal long division, and then we draw an arrow upward to show that we look at the remainder. The remainder gives us, let's delete this excess, delete the excess table, excess row. Okay, so our remainder, when you do long division, the remainder gives us the equivalent in base 2. So thus 6 in base 10. Let's see, 6 in base 10 equal to 110. So we in base 2. We look at the number we pick a number from bottom up, the arrow facing up. So it's not 011, it's 110. So we do long division. 2 goes in 6 3 times, no remainder. 2 goes in 3. So 2 goes in 3 1 time, remainder 1. 2 goes in 1, no time, and remainder 1. So 6. So let's try something else. If we've converted 6 from base 10 to base 2, let's try 11. Converted 11 in base 10 to base 2. Let's extend the table. It's probably going to take a lot. Let's erase the remainder. So 11, we want to convert 11 to base 2. shift the arrow down a bit. 2 goes 11, how many times? I think 5 times, remainder 1. And 2 goes in 5 twice, remainder 1. 2 goes in 2 once, remainder 0, no remainder. And then 2 goes in 1, not 0 times, remainder 1. So I think we can delete the excess rows in the table. So let's duplicate this. So say does 11 in base 10 equal to 1011. So we pick the values from the bottom up, from the last row to the top. So I'll show you where you can convert. You can use calculator to convert, to do the conversion to confirm. So you check the programmer aspects, you click on the settings there. Under programmer, we have X deck oct binary is base 2. So 6 in binary, you see 0110. Click on decimal is base 10, binary is base 2. So see here that 110 base 2, decimal base 10. So let's check 11 in decimal. Click on binary, 1101. See that we've confirmed, we've used our calculator to confirm that our conversion is correct. So if we do any conversion from base 10 to base 2 manually, you can use the calculator, the inbuilt calculator of your PC, of your Windows, especially Windows 10. You can use the calculator to confirm whether your manual conversion is right. So let's try something else. 1011 in base 2 to base 10. We want to convert now from base 2 to base 10, the other way around. So the method will be quite different. It won't be long division like we used before. Long division was the method we used to convert base 10 to base 2. So doing the conversion the other way around. Let's get out the table. Let's bring out the table. It's going to be slightly different. Let's adjust the layout. Then while you fill the table 1, 2, 4, 8, that should be 8, and then 16. So you fill the table from left to right, 1, 2, 4. Now, how do we get these values? They are all powers of 2. So I think I probably should put that in here. Insert it, the row above. 2 raised to power 0. 2 raised to power 0 gives us 1. 2 raised to power 1 gives us 2. 2 raised to power 2 gives us 4. Then 2 raised to power 3 gives us 8. 2 raised to power 4 gives us 16. So see, they're all powers of 2. So you arrange powers of 2 in increasing order from right to left as you have it. 1, 2, 4, 8, 16. So depending on the number of characters you have in your binary number. So that's 1, 0, 1. So you write it from right to left, 1, 0, 1. From right to left, 1, 0, 1. 1, 0, 1 from right to left. So enter that value there. Then 1, 0, 1 equal in base 10. You want to get 101 in base 10. You want to get the equivalent in base 10 from base 2. So you multiply 4 times times 0, 4 plus 0 plus let me adjust that. So you're going to multiply. You multiply the values on the second row and the last row. So 1 multiplied by 4 plus 0 multiplied by 2 plus 1 multiplied by 1. So we are multiplying the values on the last row with the corresponding values in the middle row. So that gives us 4 plus 0 plus 1. That equals to 5. So that's the equivalent in base 10. In base 10. So 101 in base 2 equal to 5 in base 10. So 101 in binary form equal to 5 in decimal form. So let's see. So we convert base 101 in base 2 to base 10. We get that. We get 5 in base 10. So if you try 1011 in base 2, 1011 in base 2 to base 10, let's see how different that will be. Let's delete that. So we enter from the right 1 1 0 1 1 0 1 1 and from base 2 to base 10. Then let's see, you're going to repeat what we did earlier. You're going to repeat it. You say 1 0 1 1 in base 2 equal to, so multiply the last row by the middle row. 1 multiplied by 8 plus 0 multiplied by 4 plus 1 multiplied by 2 plus 1 multiplied by 1 will be equal to 8 plus 0 plus 2 plus 1 equal to, that will be 11. So 11 in base 10. 11 in base 10. So we see here that 1011 in base 2 is the same thing as 11 in base. Let's confirm with our calculator. Erase, clean, binary. Let's click on binary 1. Now if you didn't see that in binary, all the other numbers apart from 1 and 0, all the other numbers are there. And we click on decimal 0 1 2 3, all the numbers are visible. 0 to 9 are visible. If you click on hexadecimal, above the numbers you can have letters A, B, C, D, E, F. But for now we won't worry about hexadecimal format. In decimal is 0 to 9. In octa is 0 to 7. In binary it's just 0 and 1. So 0 and 1 alone. There's no 2, no 3 in binary, so it's just 0 and 1. So 1 0 1 0 1. We've done that before. In decimal, in binary is 5. 101 in binary is 5 in decimal. So let's try the other one. Click on binary again. 1011 in binary. Click on decimal. That's 11. So we've confirmed that our conversion was right. Our manual conversion of 1011 in binary format of base 2 to base 10 is actually 11 in base 10. So let's get rid of the screen and go to another subtopic. Developing the input combination. Developing the input combination of a truth table. Developing the input combination of a truth table. Now, there's no need to cram the input combination of a truth table. It's really easy to develop all the possible combinations for the input of a digital system or a digital circuit. So for a digital input or for a single input circuit, digital logic circuit, you can, for a single input, single output, let's look at how to generate the truth table, the input combinations for a truth table. Remember we said last week that when you're developing a truth table, the input combination, your input has to show all possible combinations. So if it's just a single input, single output, let's draw a table of the sort, single input, single output, layout. Let's justify it to the center. Simple equals simple output x and y. Let's assume that our input is x, our output is y. So if you have a single input, a digital system, a digital logic circuit that's a single input and single output, this is how your truth table should look like. So let's Basically, the only gate that has single input, single output is a NOT gate, an inverter. So let's drag it out. Let's insert the text box. X, put X value there. X value, X value, and X value. Zoom in a bit. X value. So X, we adjust the X. So we have single input X, and our output Y. So unlike most of the other logic gates, you have at least two inputs. A NOT gate has a single input. So a NOT gate is an example of in how to create this simple logic circuit with single input, single output. If you have single inputs, your combinations can either be 0 or 1. It's either your input is 0 or 1. So the truth table for single input, single output will have just two values, either 0 or 1. Then the output will depend on the type of gate. But since it's not gate, we know that it will just be the opposite, 1, 0. When you have 0, the input is 0, the output is 1. If the input is 1, the output is 0. So NOT gate it inverts whatever you have at the input. So this is the truth table of a simple or a single input, single output logic circuit. Your input can either be 0 or 1, and your output would be corresponding to the input. So for a single input, single output truth table, we have 0 and 1. So let's go for two input, single output logic circuit, two input, single output. Our truth table will be slightly different. This time around, let's increase the number of columns to three columns and multiple rows. Let's change. We can erase some rows. Right click, delete rows. Let's adjust the design of the table. Let's justify layout, center, align at the center. In input, you can have X, Y. Since it's two inputs, you use X and Y as inputs, and maybe Z as output. So you can use A, B, and C, depending on. You can use any letter you want for the input and output. So let's use an AND gate as an example of a two input, single output logic gate. It can be OR gate, it can be AND gate, it can be NAND gate, or NOR gate. So A and B as our inputs, then C as our output. A, B, and C. A, B, and C, AND gate. Let's move this. We can create a copy of this. Delete to replace. Let's put in an OR gate. An OR gate can also give us two input, single output logic circuit, where A and B are the inputs and C is the output. So it can also be a NAND gate or a NOR gate. You notice that the number of rows for its two inputs. Okay, let's go 0011. You start by using if it's two inputs, then you use 2 zeros, 2 ones. Delete the extra row. 2 zeros, 2 1, and this is single 0, single 1, single 0, single 1. So for every two input single output logic system, the input combination will always be of this nature. Now, whenever you have a two input single output, the input section of a truth table will always look like this. The A part will always have 2 zeros and 2 ones. The B part would will be interchanged, or will oscillate between 0 and 1, 0 1 0 1. So now the output C is determined by the type of input gate, two input logic gates or logical circuit. So but the input A and B is constant. If you have a two input logic circuit, the input will always look like this. This is all the possible combinations you can have if you have two inputs. So the output is only what is the only thing that will vary. The input A and B will always be constant, will always look like this. So you don't have to cram it. It's basically simple to generate. The A part, you have two zeros, two ones, and the B part, you alternate between zeros and one. That's pretty easy. So the output will be determined based on whether it's an OR gate or an AND gate. So let's go to three inputs. Three inputs. I'll show you how to generate the input combinations for a three input single output logic circuit. So this time around, of course, the input would be 3 instead of 2. So we have A, B, and C, and the number of rows will be more. You have more rows than when you had two inputs. So A, B, C, and then D will be the output this time around. So A, B, C input, and D is the output. So let's delete this. We replace the two inputs OR gate. We'll replace it with a gate that has three inputs. So now let's search for three inputs logic gates. Three inputs logic gate, three input logic gates, and let's check. Nope, it's not here. 7400 series. Three input AND gate. So a three input AND gate. Let's rearrange our inputs to fit the gates. A, B, and C will be our inputs, and D will be our output. And D is our output. So we'll be generating all the possible input combinations. If you have any logic circuit that has three inputs, the input A, B, C will always look like this. So we have four zeros. Before it was 2 zeros, now it's 4 zeros and 4 ones. 4 zeros, 4 ones. That's the most exterior one. 1 2 3 4, 1 2 3 4. Delete the extra 2. Then 2 zeros, 0 0 1 1 0 0 1 1. Now C will not be 0 1, alternating 0 1 0 1 0 1 0 1. And then the output will be determined based on the type of gate. If it's an AND gate, the output D will be different. If it's OR gate, the output will be different. But the inputs A, B, and C will always be constant. It will always look like this. The most exterior one is 4 zeros, 4 ones. Then B, 2 zeros, 2 ones, 2 zeros, 2 ones. And then the C will be alternating between 0 and 1. So if you want to create the input side of any logic circuit, and it's 3 input, this is how it's going to look like. So now representing a decimal, the decimal, that's the base 10, representing the base 10 equivalent of binary input. Now we see this binary input 0 0 0 0 0 1 0 1 0 in binary. What do they mean in decimal form? So like I said, sometimes when it's good to convert binary to decimal, so humans can better understand the data, what data stands for. So if you have A, B, and C, if you combine A, B, and C together, such that the first in base 10, we want to see what A, B, and C together in base 10, what it stands for. So 0 0 0, what is that in base 10? Let's get subscript. I want to write base 10 in subscript form. Base 10, A, B, C in base 10. Let's remove that. A, B, C in base 10. So 0 0 0, what is 0 0 0 in base 10? What is 0 0 1 in base 10? What is 0 1 0 in base 10? What is 0 1 1 in base 10? What is 1 0 0 in base 10? That's what I want to do. So let's go to calculator, binary section, delete. So 0 0 0 0 is still 0. is 0 in binary, is 0 in hexadecimal. So 0, 0, 0 is 0 in base 10. Let's try 0, 0, 1. 0, 0, 0, 1. That's binary in base 2. In base 10, it is still 1. So it's 1. This is 1 in base 10. Let's go back to the calculator. 0, 1, 0, 0, 0, 1, 0, 1, 0. Sorry, that's wrong. 0, so 1, okay. Listen, there's a problem somewhere. Okay, yeah. I click on the decimal. It's in decimal binary. Make sure you click on binary first. 0, 1, 0. So that's in binary. In base 10, it is 2. Decimal is 2. So this is 2 in base 10. Next, 0. Let's click on binary again. Clear the screen. 0, 1, 1. 0, 1, 1 in binary is 3 in base 10 or decimal. That's 3. The next one, you want to convert 1, 0, 0. 1, 0, 0. Okay, we are still in decimal. Let's delete, go back to binary. Make sure you give 1, 0, 0 in binary, convert it to base 10. That's 4 in base 10. The next 1, 0, 1. Click on binary, clear the screen. Remember, look at 1, 0, 1. It's only 1 and 0 that's appearing. That's decimal 5. Clear screen, binary 1, 1, 0, 1, 1, 0. That's 6 in decimal form. It is 6, not 5, 6. Then last but not least, let's clear the screen, click on binary. 1, 1, 1 is 7. So you see here that it's actually increasing 0, 1, 2. So when we make our arrangement like this, we are actually increasing in decimal form. It's actually an increment of numbers from 0 to 7. So see that the decimal form helps us to understand what the arrangements we've been doing. So when we create a truth table, our input is actually increasing from 0 to 7. That is, if it's a 3 input logic circuit, we are feeding 0, the decimal 0, decimal 1, decimal 2, decimal 3. But in binary form, it might not be easy for you to understand or see that that's what you are doing. But if you convert it to decimal, you see that you're actually feeding in numbers 0 to 7 in decimal form. So for 3 input AND gate, for a 3 input AND gate, where A, B, C are your inputs and the D is the output. Let's create a text box. Yeah, text box A, input A, B, and C, then output D. Let's see, we can create a small mini truth table here. Like I said, remember that your A will have 4 zeros and 4 ones. 4 zeros, another 0, another 0. You don't have to cram it. It's just by the other ways you can arrange it, but this is the easiest way to arrange your input, your total combination for 3 inputs. The easiest way to arrange it such that you won't have to cram anything. So just know that if you say for 3 inputs, the A or the first input will have 4 zeros and 4 ones, 4 zeros and 4 ones, 4 zeros, 4 ones. Let's adjust this, raise it up a bit. 4 zeros, 4 ones. Let's zoom out a bit. 4 zeros, 4 ones. Then 4 zeros, 4 ones. And the next input after the one with 4 zeros and 4 ones, we'll have 2 zeros and 2 ones. 2 zeros, 2 ones, until it fills up the total space. So 2 zeros, 2 ones. 2 zeros, 0, another, no, sorry, 0, 0, 2 zeros, 2 ones. Then again until it fills up this space beneath it. Another 2 zeros and 2 ones. 2 zeros, 2 ones. Then the last input, which is input C, will now be alternating between 0 and 1. 0, 1, 0, 1, 0, 1. So see here that we are moving from 1, 0, 1, 1 to 2 zeros, 2 ones to 4 zeros and 4 ones. So result is a factor of 2. 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2. So that's single zero, single one. Let's adjust that. Yeah, single zero, single one, single zero, single one, 10, 11, 10 until you fill up the space. So basically, all possible combinations for a 3 input as shown by A, B, and C. This is how you want to combine A, B, and C with ones and zeros, that it will not give you at least one of these values. So this is all the total number, all the permutations of a 3 input logic circuit, where each input can either be 0 or 1. So if your A, B, and C can either be 0 or 1, the total number of ways you can arrange it based on permutation is as shown by this truth table. So the A, B, and C of a 3 input logic circuit, or the 3 inputs your logic circuit, is constant. The A, B, and C, they are always constant. The inputs A, B, and C, they are always arranged this way. You can arrange them in another way, but basically all the values are contained here. So the output D is as determined by the output D is as determined by the type of logic gate or logic circuit. So since this is an AND gate, the output D will be determined by the characteristics of an AND gate. And if this were to be a 3 input OR gate, the output D will be different. But notice that the A, B, and C remains constant. The input, this input is showing that regardless of how you arrange your logic inputs in ABC, the values will fall within the values shown in the first 3 columns of this truth table. Is either all 3 are zeros, ABC is 0, or one of them is 1 and the rest are 0, or any 2 is are 1s and the last one is 0, or all 3 are 1s. So you see here that if you run simulation, we did this last week. Let's just it's only when ABC is 1, all 3 are 1, that the output is 1 for an AND gate. We've done this last week. Once any of them is 0, D becomes 0. So you can easily feel, we did this last week, so I won't waste too much time on it. So 0, 0, 0, 1. So that the D was determined by the nature of the gates. So 0, 0, 0, 0, 0, 1. So it means that if you feed decimal 0 to a 3 input AND gate, the output is 0. If you feed decimal 1, 2, 3, 4, 0 to 6, if you feed 0 to 6 to a 3 input AND gate, your output will be, it's only when you feed decimal 0 to a 3 input AND gate that the output will be 1. So that is the significance of we converting from binary to decimal, showing the response of an AND gate to the decimal numbers. So let's switch. Let's go to another topic. Let's go to the Boolean algebra. Boolean algebra. We've spoken extensively on truth tables, on how to create the input combinations for your truth tables depending on the number of inputs you have. If it's 2 inputs, the way the truth table will look like. If it's 3 input, the way the input will look like. If it's a single input, the way the input combinations for your truth table will look like. So let's go to Boolean algebra. It's a mathematical notation or representation of logic gates or logic circuits, or digital logic, or combinational logic circuits. So we've been using the gates themselves, using truth tables when I want to do something called Boolean algebra. So it's a way of mathematically representing logic gates or logic circuits. So I'm sure you must have done something like this last semester. So this should be familiar as we go over the terms and the definitions in Boolean algebra. As we look at some examples, you should be familiar. Since you did this last semester, you did this in a theoretical course last semester. So we'll be doing more of simulation with the Boolean algebra examples. So it will just be the theory as you did last semester. We'll do some simulation so you see the significance of how Boolean algebra can be used to express the relationship between the input of a combinational logic circuit or a digital logic circuit and the output. So for a 3-input AND gate, you see D equals to A dot B dot C. For an AND gate, you use dot notation. Dot notation. For an AND gate, we use dot notation. This should be, we must have done this last semester, so I don't think I should spend too much time on explaining that, but I'll still go over it for those of you who might have forgotten. So for a 3-input AND gate, D equal to A dot B dot C. So the dot notation shows that the gate is an AND gate. Now the dots, actually this dot is preferably a tick dot. You don't not like full stop, but if you use a full stop, it's welcome. It still goes. You can still use a full stop, but actually if you're writing this down with paper, it's better to use this kind of dot. So it shows that this dot is actually different from a full stop, but because of the fact that it's probably not that dot is not on the keyboard, so you can use a normal full stop, to notify or to represent an AND gate. So let's go to the next gate. For an AND gate, you use dot. It's dot notation. So A dot B dot C, you are showing it shows that A, B, C are connected by an AND gate. So A dot B, once you see A dot B dot C, you know that okay, there's an AND gate that is connecting, or A, B, and C are inputs to an AND gate. So your Boolean expression or Boolean equation it helps you to represent logic circuits mathematically, such that if you see a Boolean expression, a Boolean equation, you can design a circuit, you can draw a logic circuit just from the mathematical expression as shown by the Boolean equation or Boolean expression. So if you see a Boolean expression or a Boolean equation, you can draw or design the logic circuit that the Boolean expression represents. Or instead of even drawing a Boolean, drawing a circuit, rather drawing a digital circuit or a combinational logic circuit, you can just use Boolean expression to represent the whole circuit. It's concise, it's compact. So we've done that for AND gate. Let's go for OR gate. Now, by convention, it's always better to write AND or OR in capital letter to show that it's not just a normal AND if you are representing the gate. So for OR gate is A plus B capital B plus capital C. So for an AND gate we use dot notation. For OR gate we use plus. So this shows that A, B, and C are connected to an OR gate, a 3-input OR gate. We use the plus notation. So if it's a 3-input OR gate, we use plus notation. A plus B plus C. I tried searching for a 3-input OR gate here. Surprisingly, I could not find any. Probably I didn't search well. So let's go to the next one. Let's go to NOT. The NOT gate. Remember, for if it's an OR gate, use plus. A 3-input OR gate, use plus notation. A 3-input AND gate, use dot notation. So let's go for NOT gate. The NOT gate. Remember, NOT gate has a single input and single output. So probably you can make A our input and B our output. Input A. This time around, B will not be an input. B will be an output. B will be output. A will be input. So we've seen the Boolean expression for 3-input AND gate and 3-input OR gate. So let's go for a NOT gate. NOT gate has single input and single output. And so A is our input and B is our output. Remember that in NOT gates, it inverts whatever you feed at the input. So it's represented by a bar. You place a bar. Okay, I'm looking for a notation in PowerPoint for that, to place a bar over a character. The only thing I can find is strike through. It doesn't work. Let's erase that. Okay, you got underscore, something like this. So this is a crude way of doing it. Actually, there's a more sophisticated way of doing that. Yeah, well, probably I'll do that later. But crude way is probably to just use underscore. add another score object and place it over. So okay, I didn't write that well. B is actually a bar. So the output B is the opposite of whatever A is. So you represent a NOT gate B equal to bar A. You place a bar over it to show that it's a NOT gate. You are inverting whatever A is. If A is 0, B will be 1. If A is 1, B is 0. So you represent a NOT gate by using a bar notation. You place a bar over the input. That shows that we are using a NOT gate. So that's notation for a NOT gate. You use a bar. For an AND gate is dot notation. For an OR gate is plus notation. For a NOT gate is a bar notation. So if you treated the Boolean expression or Boolean representation for AND gate, 3 input AND gate, 3 input OR gate, and we've done the one for a NOT gate. So let's go for the next one. You want to get the Boolean expression or Boolean equation or Boolean expression or equation for an exclusive OR gate. So this is an exclusive OR gate. An exclusive OR gate, that's 2 inputs. Exclusive OR gate has 2 inputs, not 3 inputs, 2 inputs. A, B, and then C will be our output this time around. Inputs A and B and output C. So we want to generate the Boolean equation that expresses the relationship between the input and the output of an exclusive OR gate X or. Now all your gates, you see here, I consistently use all capital letter. AND gate all capital letter or all capital letter not, to show that it's not just normal English words like and or not. When you make it all caps, you show that it's gate. We are talking about the gate, so it's better to follow that convention. Whenever you're writing AND for gate, you use capital or not or XOR. So now for exclusive OR, the notation is like plus, but it's different. I'm trying to let me see if I can get the symbols in PowerPoint. General punctuation, Armenian, Cyrillic symbols, Greek and Coptic symbols, Cyrillic symbols. I'm trying to search for if I can see exclusive OR symbol here. Spacing, Latin extended symbols, or Latin basic Latin characters. Basic Latin characters are English characters actually. Latin supplement, Armenian. Well, probably I didn't search well, but I can't find the exclusive OR character here. I probably have to improvise. I can improvise and create my own exclusive OR notation. It's actually an O that surrounds a plus. An O that surrounds a plus. So let me increase the font size of the O, make it larger a bit. Let me see how can I do this. Increase the size a bit, increase the O a bit. Plus. So you place a plus inside an O. Yeah, something like that. I thought it was going to be a special character that there probably could be a special character that looks like this, but can't find it. So let me group them together. So let me delete this plus sign. So exclusive OR symbol looks like this. Create more space. Exclusive OR symbol looks like this. Yeah. So whenever you see this symbol, it means that you are using an exclusive OR gate. So this is the notation for exclusive OR gate. So treated NOT gates, 3 input AND gate, 3 input OR gate, exclusive OR gate. So we've shown the Boolean expression or Boolean representation for a 3 input AND gate, a 3 input OR gate, a NOT gate, and an exclusive OR gate. So let's see if we can get another gate and show the Boolean expression or the Boolean equation that expresses the relationship between the input and the output. So let's go to 3 inputs NAND gate. The 3 input NAND gate. How do you represent a 3 input NAND gate in Boolean expression or with the Boolean equation? So I'll just copy. It's actually similar to 3 input AND gate. Just copy, paste 3 input NAND, capital N. Yeah. The only difference, in fact, it looks so much like an AND gate. The only difference is that bubble, that small bubble in front of a NAND gate, shows that there's a NOT. There's a NOT at the output of a NAND gate. So we just place a bar. We place a bar over what should be the normal output of an AND gate. So I use multiple underscores using a manual way, a crude way of doing this. So for a NOT gate, you see that we place a bar over the input. This time around, we place a bar over the whole input. So the difference between a NAND and an AND gate is just a bar. That small bubble in front, is an AND gate followed by a NOT. It's a small NOT gate in front of an AND gate. That's what makes up a NAND gate. So you place a bar in front of it, in front of the AND gate. So let's go for a NOR gate, a 3-input NOR gate. So a 3-input NOR gate is just an OR gate followed by a NOT gate, a small bubble there. That small bubble in front is a NOT gate. So we copy a 3-input, the expression, Boolean expression for a 3-input OR gate. We copy it and capital N, and we just place a bar. That's the only difference there. Just place a bar to cover the whole input. That's all. That's the difference between a 3-input NOR gate and a 3-input OR gate. Is that NOT, that small NOT in front. So D equal to, now I want to show, you go to equations, click on equation. I want to show how to place a bar the sophisticated or the standard way of doing it. Under accents, you find one option that has a bar. You click on it, A plus B plus C. Click. So this is the standard way, the Microsoft way of doing it, instead of the crude method I'm using to place the bar. So, well, either one works. You can use that method. You can insert the equation yourself, or you can just use underscore. But I assume that you'll be writing this down, so it doesn't matter. So that's that about that. We've represented in Boolean expression or using Boolean equation AND gates, NOT gates, NOR gates, exclusive OR gates. So let's go to the next one, exclusive NOR gate. So there's exclusive OR and exclusive NOR gate. The difference is just that small bubble. You are placing a NOT in front of a NOT, placing a NOT gate, small NOT gate in front of an exclusive OR gate gives you exclusive NOR gates. So just place that bar, small bar, that bar to cover the whole input basically. So when there's a NOT in front of a gate, a logical gate, basically if you want to represent that in Boolean expression, you just use a bar. You place a bar over what should be the normal expression defined by that. So we spoke extensively on Boolean expressions and Boolean equation. Let's go to the next thing we're talking about, next subtopic for today. I'll be going through a little textbook, like textbook or lecture guide, to see what else we'll talk about. We've talked about AND gate, NOT gate, representing logic circuit, truth table. A NOT gate is also called an inverter. We've said that before. Y is only true if A is true and B is true. That's all gates rather. If A or B is true, we've done this before. We've done NOT gates, NOT AND, that's NAND. We've done this part. NOT or OR gate. NOT, you combine NOT and OR gate, you get a NOR gate. Look at the Boolean expression right there. Now let's look at this boiler example. It said if a chimney is not blocked and the house is cold and the pilot light is lit on, they open the main valve to start the boiler. So B is represented input, chimney blocked. Now they put a NOT gate, so chimney not. So if chimney is not blocked, and then C, house is cold, and then P, pilot light is on, then the output open fuel valve. So we want to start a boiler. If you want to create a small digital logic circuit to control the boiler in your house, that probably will not apply to Nigeria because we don't have winter here. For places where there's winter, you want to have a boiler in your house to create heat. So if the house is cold and chimney is not blocked, then start the boiler. So you can create a digital logic circuit that would automatically start up a boiler if some conditions are met. So if something is true in digital form, that is 1. If it is false in digital form, that is 0. So 0 is false, and 1 is true. 1 is true, 0 false. So you want to recreate that circuit. The circuit to control the boiler of your house on a winter night. You start with a NOT gate. We use NOT gate because we want to. The NOT gate is that we want for the chimney being blocked. We desire only when the chimney is blocked. It's not blocked, rather. Sorry. If A represents that chimney is blocked, so we want to invert it. So if chimney is blocked, if that is true, A is 1. When A is 1, it means that the chimney is blocked. So we use an inverter to convert it. So when A is A represents the chimney input. Let me just connect it first. And the output. So we want to invert the chimney input. We invert the chimney input. So they used to be for theirs. I've just, for consistency's sake, I think since we'll be using A, B, and C for our own inputs, let's follow our own notations. So the B and C input are connected directly to the AND gate because we are not inverting. Their input is, I think the second input is B here. For our own B is that the house is cold. So if house is cold, that means B is true. That means B is 1. If house is cold, B is 1. Delete, click, connect. So the chimney, we want to invert the chimney input. The other inputs will be connected directly to the AND gate. So chimney A connects, D is the output. The output D is the valve. The valve will turn on the boiler. So there's a valve that's controlling the boiler. The boiler comes on. Now, before we continue, let's put the correct Boolean expression here. So A here, see that B, C, P. Ours is A, B, and C. A, B, C. So this A, the output of this NOT gate here would be A bar. We place a bar over the A to show that the A has passed through a NOT gate. So let me see if I can position this bar correctly. Okay. So the chimney input will be inverted. So when the chimney is blocked, A equals A dot. Let me just put the correct. So let's put the correct Boolean expression or Boolean equation for the output. A dot. Remember that AND gate is dot notation. You place a bar above. So it's not normal A again because A has been inverted. A has become A bar now. So it's A bar dot B dot C. Normally it should be A dot B dot C. But before the A got to the AND gate, we inverted it. So that's why we have A bar dot B dot C. So let's look at the corresponding truth table. So if you want to do the truth table for this digital logic circuit, we have to create another row for A bar. Because we can't combine A. We can't use A as it is because A is no longer the input to that AND gate. It has now become A bar. So we will create a new column for A bar. Create a new column for A bar. Let me see, where can I put it? And we definitely need to erase the outputs for this. So let me copy the bar. You can place the A bar after the A. So A, B, and C are the normal inputs. They are the inputs to the digital system. The A bar has now, it's an input inside the logic system, the logic circuit. So I've erased the former output. So A bar will just be the opposite of A. So wherever you have 0 in your A, it becomes 1. 0, 0, 0, 1, 1, 1, and this is 0, 0, 0. So it's basically opposite of what you have in A. So A bar is an input inside. It's not visible on the outside again. So A, B, and C are the inputs, the overall input to the system. But inside you have a conversion. One of the inputs, which is input A, has been now converted to A bar this time around. So let's down. So A bar A bar is directly affecting the output D, no longer A. So let's complete our. Oh, sorry. Let me. This is not coming out right. Okay, let me start again. Our improvised table. Let's complete our improvised table. Output D is now controlled by, before it should be A, B, and C. Now it is A bar, B, and C. A bar, B, and C. That determines what our output D will be. So now if you use, let's simulate. If we run our simulation, although we can do this without simulation, but let's just do it. Now, when A is 1, instead A bar becomes 0. When B and C are 1, so it's only when B, C is 1 and A is 0 that our output is 1. See that once our output A is 1, the output becomes, so only when A is 0 and B and C are 1, that is only when the D is 1. So every other value, D is 0. D is 0 apart from when A is 0 and B and C are 1. So when A is 0, A bar becomes 1. So A bar, B, and C are what determines the value of D. So A bar, sorry about that, A bar is 1, 1, 1, 0, 0, 0, 1, 1, 1, 0. So it's the opposite of what you have in A. A is 0, 0, 0, 4 zeros and 4 ones. A bar is not the opposite of that, 4 ones and 4 zeros. So when B is 0, C is 0, and A bar is 1, D is 0. If you want to confirm that, just run the simulation. But basically, if you follow the truth table for an AND gate, the standard truth table for an AND gate, you see that it's only when all the inputs are 1 when the output is 1. So when A is 1, A bar is 0. When A is 0, A bar is 1. So when A is 0, when A is 0, B is 0. So when B is 1 and C is 1, they are fed directly to the AND gate, so they influence the AND gate directly. But when A is 0, A bar becomes 1, and then B and C, when either of them is 1, they're connected directly. So you only have one at the output when A is 0, B is 1, and C is 1. At every other point, D is 0. D is 0 apart from when you have A bar to be 0, B, and C 1, 1. So when chimney B is blocked. So when chimney not blocked, so we invert it. When chimney is blocked, B here is 1. You now use an inverter to invert it. So we want when the chimney is blocked. When chimney not blocked, B is 0. And then it inverts that and it becomes 1. So when chimney is not blocked, pilot light is on and the house is cold, the valve is turned on. So I hope you understood that. Explanation. Okay, let's move to the next one. We are still on that Boolean algebra. There are some Boolean algebraic laws. There's some Boolean algebraic laws you want to consider. Some Boolean algebraic laws. So we are done with our mini circuit that is used for controlling boiler operation on a winter night in a temperate region. The A input here represents the chimney, when the chimney is blocked or not blocked. B and C. B represents the whether the house is cold, and C represents the pilot light. So when the chimney is not blocked, so you put a NOT gate when it is not blocked, and when the house is cold, and look at the keyword there is and, so that means I'm going to use an AND gate. If it were to be or, if chimney is not blocked, or when the pilot light is on, or when the house is cold, then we would have used an OR gate. But since it is AND, we want all three conditions to be met before the VAT, so then we use an AND gate. So I hope you got the difference between when we have to use an AND gate or an OR gate for your digital logic circuit or combinational logic circuit. So let's go to our Boolean laws. Our first Boolean law, they said a plus 1. So we want to prove a plus 1. So if our a can be 1 or 0, we know that. Stop. Now if our input here, sorry, a plus 0, not a plus 1. If our second input is 0, that means we won't change the value. So what happens if you had a and 0 together? Let's switch your logic levels. 1. If you use a plus 0, is that regardless of what happens, it mirrors the output. Let me erase this. And let's go to Boolean laws, Boolean algebra, examining some Boolean laws. Let's examine some Boolean laws. The first one we want to examine is a plus 0. What happens when you had a Boolean input, or sorry, a digital input to 0? A plus 0. What happens? So according to the law, it says that a plus 0 is a. So if you had an input to logic 0 using an OR gate, the output will always be a. Whatever you have, your a will reflect in the output if the other input is 0. So a plus 0, remember that plus notation shows plus notation is OR gate. So if you combine your input a with logic 0, the output will always be a. So let's prove that. If inputs, normally for a 2 input logic circuit, you use a b c, where a and b are input and your c is your output. So but this time around, b will be replaced by 0. We replace b with 0, permanently 0. So our a can be 0s or 1. Normally you should have 2 0s and 2 1s. 2 0s, we treated this earlier today. 2 0s if you have a 2 input logic system or logic circuit, 2 0s, 2 1s, your a b2, and your b should be 0 1 0 1 normally. But this time, since the input is 0, it's permanently 0, so we can't have 1 since our second input is 0. We've grounded it directly to 0. So what would our output be? What would output be if one input is a and the other input is permanently 0? So according to the law, it should be the same thing. Our c should be exactly a. A plus 0 should be a. So that means our c, our output, should be a. It should reflect exactly what you have in a. Where a is 0, c should also be 0. Where a is 1, c2 should also be 1, according to this law that a plus 0 is a. So if you had a to 0, it should give you a. If you add a to a, it should still give you a, according to this law. So we can prove it by running the experiment. If you had a and a together, a plus a is a. According to Boolean law, a plus a is a. We can prove that law by running a simulation in our virtual laboratory. Let's run a simulation in our virtual laboratory to prove that a plus a is 0. So let's delete 1. Let's connect a to the 2 inputs are connected to a. The first input is a, second input is still a. We bridge a on one point. From one point, you bridge it to the other point. So a plus So the Boolean expression for the output is a plus a. At this stage, the output here is a plus a. So we added both inputs are a and a, not a and b, but a and a, because a is connected to both inputs. So it is a plus a, rather, not a and a or a rather. So a plus a. So here we have a plus a. According to Boolean law, a plus a is still a. So the second part of the input is a. So let's view the truth table. We have a on both sides, a and a on the other side, not a and b. So c equal to a plus a. So according to Boolean law, a plus a should still give us a. A plus a should give us a. So let's prove that. Let's see what we can do. A plus a should give us a. Now a can either be 0 or 1. A can either be 0 or 1. It has just two possible values, and there's probably no need for this truth table to be this long, since the number of values, the possible combination is reduced. So let's delete rows. A can either be 0 or 1. That is all. It can be 0 or 1, 0 or 1, 0 or 1. So let's delete this row. So a can be 0 or 1. Good Lord said, let's prove, run. Now when a is 0, what happens? C is 1. So C is 0. When a is 1, C is 1. So a and c, they follow together. It's the same value, 0 0 1 1 0 0 1 1. Let me shift this. A plus a is blocking our view. Let's shift it up a little bit. Run it again. So when a is 0, c is 0. When a is 1, c is 1. We see that c is actually equal to a. The output is the input, is the same thing. So we've proved that when a is 0, c is 0. When a is 1, c is 1. So that means a plus a is equal to a. So we've proved that a plus a equal to a. We've proved that this law is true by running an experiment. We ran a very small virtual experiment to prove that a plus a equal to a. We have proved that algebraic that Boolean algebra law. The next one is a plus 1 equal to a. That is another law we want to prove. We want to prove that if you add a digital input a plus, if you add it to 1, you will still get a. So let's see. Now the second input is a 1, rather we change this to 1. The first input is a, second input is 1. So it means that the second input is permanently 1, while the first input a can either be 0 or 1. A can be 0 or 1, while input 1 is actually permanently 1. So let's connect the second input to 1. We've disconnected disconnected a from the second input. So we'll make the second input permanently 1. So you clicked on it to make it permanently 1. I've enabled it. It's not permanently 1 now. We will not change it. Only permanently 1. So the Boolean expression for that will be a plus 1 this time around, not a plus a. A plus 1. Click on logic levels. Run simulation. So a is permanently 1. Sorry, 1. The second input is permanently 1. It's not changing. It's permanently 1. It's not changing. So we are going to be altering a. Now let's see. Click. Regardless of what happens to a, our output is 1 actually. So when a is 0, c is 1. When a is 1, c is still 1. So c doesn't change because, and then it means that our output to be 1 actually. Sorry, the law is a plus 1 equal to 1. Sorry, not a. I made an error by stating that a. So let's go to the next law. A plus a bar equal to, I think, 1. That is the next law we want to prove. We want to prove that a plus a bar equal to 1. A plus a bar equal to 1. So let's create our bar manually. We can do it using the automatic equation. Well, let's do the manual way. Add the bar over the a. So a plus a bar equal to 1 according to the Boolean algebraic law. So we write a plus a bar equal to 1. So that means the second input should be a bar this time around. So first input is a, second input is a bar. Now, although this is two input system, normally you're supposed to use the normal two input combinations for the truth table. But because the input can just be 0 or 1, basically it's just one input a that you're manipulating. That's why we are still using only 0 and 1. So where A is 0, A bar is 1. When A is 1, A bar is 0. Our output is A plus A bar, actually. A plus A bar this time around. So you want to prove that it's 1. You want to prove that A plus A bar is 1. So to how do we create A bar? Let's go to our truth table. How do we create A bar? We use a NOT gate. So let's delete the second input and put A bar there. Delete this guy, or you drag it down. Let's move this input forward. Move it back a bit. Move it back a bit. Delete the extension. So we get a NOT gate. So we feed a NOT. We use a NOT gate to create A bar. We want to create A bar. We want to feed A and A bar to the two input OR gates. So let's do for a NOT gate, OR logic gate, inverter. NOT gate is also called inverter. So we place a NOT gate here. Place a NOT gate here. Click and drag backwards. Click and connect. Click connect. So we connect A directly to one input, and we connect A through a NOT gate to the second input. So we have A on one side and A bar on the other side. So A here and A bar on the other side. We create our A bar manually using underscore. Underscore, click, drag, place A and A bar. So the output is A plus A bar. A plus A bar. A plus A bar. According to Boolean law, A plus A bar should give us 1. Should give us digital output 1. So we want to prove that by running a little simulation to prove that Boolean law, that A plus A bar equal to 1. Okay. So let's go to logic level. Let's run the simulation. Now when A is 0, C is 1. When A is 0, see that A bar is 1 when A is 0, but the output is 1. If you click on that again, that A is 1 and A bar is 0 this time around, C still remains 1. So regardless of your input, as I change the input, the output doesn't change. The output is permanently 1. So this proves that A plus A bar equal to 1. So we have proved this Boolean law by running a virtual experiment. So output 1 1 regardless of the input. Let's go to, so we are done with all the laws that have to do with OR gates. Sorry, yeah, OR gates for 2 inputs. Let's go to AND. Let's go to AND. We've proved those laws. Let's prove some other laws. Let's prove the other side of the laws. The next law you want to go from bottom up this time around. A dot A bar equal to 0. We want to prove that that law is correct, that law is true. A dot notation, that's AND gate. A dot A bar is 0 according to this law. A dot A bar is 0. So you want to prove whether, you want to confirm whether it's right or wrong. So A is 0 or 1, A bar is 1 or 0, just the opposite of A. So we just replace that gate, the OR gate, replace it with AND gate. That's just the difference. We replace the OR gate with AND gate. Click connect. I have to shift this guy up a bit. Click connect, and change the plus to dots to show that we are now working with AND gate and no longer OR gate. Let's move our bar, move that bar a bit. So A dot A bar A dot A bar should be 0. So let's erase this. It should be 0 0 0 according to, if our law is right, If we prove that our law is correct, the output should be 0 regardless of what the input is. Let's run the simulation. Run simulation. Regardless of what we do, regardless of 1a is 0, a bar is 1, of course, but the c doesn't change. C is permanently 0 regardless of the value of a. Whether a is 0 or 1, c doesn't change. C remains 0. When a is 1, a bar is 0. When a is 0, a bar is 1. They are the opposite of each other, but nothing happens at the output. The output remains 0 regardless of what you do to the input. Whether you make a 0 or 1, the output remains 0. So it proves that our law is right, or the Boolean law that says a dot a bar equals 0. That law is right. So we can put 0 in both rows. So the next law we want to prove now is a dot 1. Oh, sorry. Yeah, a dot 1 equal to a dot 1 equal to a. So a and 1 equal to a. We want to prove that law, whether that law is right or not. So a dot 1. So let's bring this forward. I think we can delete this guy. Move this forward, bring it closer, and copy and paste. Connect, click, bring this forward here, change this to 1. So this will be a dot 1. Let's delete the bar. We don't need the bar again. Delete. A dot 1. So we want to prove what happens if you have a dot 1. According to the law, a dot 1 is a. So if you combine an input a with 1, so delete the bar on top also. Delete 1, a dot 1. 1. It means that all the inputs for the second input is permanently 1. So a dot 1, delete a dot 1, delete the bar on top. So a dot 1 is a, permanently capital A. So let's prove that the law is right. We're running the simulation, logic circuits. Run the simulation. Now, when a is 0, c is 0. When a is 1, c is 1. When a is 0, c is 0. When a is 1, c is 1. So they follow each other. They are exactly the same. So a is actually equal to c. Yeah, so it shows that a dot 1 is actually still a, because whatever value you have as a gets reflected in c. So when a is 0, c is 0. When a is 1, c is 1. So that means that a dot 1 equal to a. If you combine a and logic 1 together, you have a. Using an AND gate rather, you have a. So we prove that that law is correct. Let's go to the next law. So let's go to the next law. Delete. You bridge. So you are connecting a to both inputs. So we are a dot a now. We want to prove that a dot a is a. Is the next law we want to prove. We want to prove that a dot a is. So if a is 1, c is 1. If a is 0, c is 0. So they're exactly following each other. So it proves that a dot a equal to a. So that's right. So a dot a. The second input is still a. Remove it, a. So when a is a 1 1. So basically that's it. So it's they follow each other. They are. The next law is a dot 0. A dot 0 equals 0. We want to prove that if we combine input a with logic 0, you have 0 at the output. So 0 0 a dot 0. Let's delete this row. Let's prove it first. So delete. Replace the second input. The second input will be permanently 0. Delete the a, replace 0. Click on it to make it 0, permanently 0. A dot 0 this time around. A dot 0. Run the simulation. Go back to logic levels. When a is 1, a is 0, c is 0. Regardless of what you do to a, C remains 0. A1, C0, A0, C0. So it means that A dot 0 is actually 0. So 0, 0 on both sides. So we've been able to successfully prove these laws. We've been able to prove these laws. These two inputs, or basically it's actually single input. Actually, it's not two inputs because we see A, there is no B here. So all these laws we prove, they are all single inputs with some other kind of. The first input is A. The second input is either still A bar, or 0 or 1. So it's the reason why the truth table is just 0 or 1. It's not the normal two input truth table because the input actually is 1. You only have one input. The second part of the AND gate or the OR gate is actually connected. It's always connected to either 0 or 1 or A bar or still the A again. So it's actually one input. So all these laws are laws for single inputs combined with other things. So it's not actually two inputs. So we are done with proving some Boolean laws for a single input. Actually, a single input. So we are going to, in the next one, we want to test precedence. We want to test precedence and show the importance of knowing the right ways. It's almost a bit like BODMAS, but it's not fully BODMAS, but a bit like BODMAS actually, in that AND take precedence over OR. Multiplication takes precedence, it takes priority over addition. In BODMAS, B brackets, then O off, M multiplication, division. So there's no division, of course, in digital logic circuit. AND is analogous to multiplication, and OR analogous to addition. So we want to prove that A. Let me arrange it first of all. I'll explain later. A, this should be B. And Control C, Control V, B. So you want to explain. I want to explain that if you don't have brackets in a Boolean algebraic equation or Boolean algebraic expression or circuit, if you don't have brackets there, and you have plus notations and dot notation, that's multiplication. Now the multiplication takes precedence. You handle the multiplication first before the addition. It means that in any Boolean expression or Boolean equation that contains both and OR gates, that you take AND gates first. AND gates have greater precedence over the OR gate. So here we have two AND gates and a single OR gate. So it's A and B on one side and C and D on the other side, joined together by an OR gate. The output should be, let's say, E. Let's make our output E. So at this point we have A dot B. A dot B is the output at this stage. At this stage, the Boolean expression is A dot B. At this stage, the Boolean expression is C dot D. So it's C and D at this stage, A and B at that stage. So at the final stage, at the output, the final stage is A dot B plus, because now I put a bracket here just to, for emphasis, A plus A dot B in bracket plus C dot D in bracket. So see here that two gates, AND gates on one side, A and B, or that's plus C and D, another AND gate on the other side. So that is the final Boolean expression. The final Boolean expression that represents or that describes the relationship between the input and the output of that combinational logic circuit or digital logic circuit. So we have A dot B plus C dot D on one side. Now I want to prove that this is not equal. For not equal sign, not equal symbol, nothing. That's it. Not equal. It is not equal to. Now, there's another way I could have arranged this. If I ignore BODMAS, another way I would, and that would have made it wrong. If let's remove the bracket first. What if I put the B plus C separately? B plus C. If I bracket the B plus C alone, would it give you the same thing? It's not. If I do it this way, that means I'm ignoring BODMAS, the BODMAS rule. Like I said, it's not exactly BODMAS, but it's kind of like BODMAS in that multiplication takes precedence over addition. AND gate takes precedence over OR gate if there is no bracket. But if there's bracket, you have to obey the bracket. So this circuit here, let me zoom out. This circuit on top is for A dot B in bracket plus C dot D in bracket. So you want to prove that the A dot B in bracket plus C dot D is not equal to A dot in bracket B plus C dot D. We want to prove that they're not. So let me draw the second circuit to show that they're not actually the same thing. They're not the same thing. So let's copy our inputs A. Okay, let's B and C. Copy and paste. I want to draw the second circuit to see that even from a diagram, from the circuit diagram, they are not the same. So we are going to use the circuit diagram to prove the logic circuit diagram or combinational logic circuit or digital logic circuit. We are going to use the combinational logic circuit or digital logic circuit to prove that they're not equal. That A dot B plus C dot D is not equal to A dot B into brackets or A dot into bracket B plus C dot D. So 2 AND gates, Control C, Control V. So here we see they're not equal. So I will draw the circuits for both sides, left hand side and right hand side. You see that just by looking at the circuit diagram, the digital logic circuit diagram, which can also be called combinational logic circuit diagram, from those circuit diagram of the both of them, you see that they're not the same. They're different. So look for a 2 input AND gate, 2 input AND gate. Where are thou? 2 input AND gate. Okay, 3 input rather. Sorry, 3 input AND gate. 3 input AND gate. Click connect. Click in connect. Drag. So I need input A and input D. Input A, input D. Control C, Control V, copy and paste. Drag and drop. So let me connect this side. Connect, 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 click, click, click. So let me drag this up a bit. Delete, reconnect, click, 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 click. And the output is E, not C. Sorry, it's E. The output should be E. Click, backspace, capital E. Click, Control C, Control V. Copy and paste. Wrong thing. Delete. Click. Copy, paste. I need output terminal. Copy, paste. Connect, connect, connect. Let me drag this forward a bit. I need to adjust this connection. Click, delete, or adjust. Drag. Click. Control C, Control V. So this is B plus C. At this stage, the Boolean expression at this stage is B plus capital C, B plus C. So the output of this gate, of the first OR gate here, is B plus C. So this is B plus C at this stage. So B plus C is fed to the AND gate along with A and D. So the output here is the B plus C is giving bracket. You keep it so that it's on its own. One OR gate takes care of that, B plus C. So let's expand it. So A dot A dot B plus C. I hope you can see that dot is very faint actually. I hope you can see the dot. I can't make it bigger than that. Weird. Okay, there's a dot there. I hope you can see that dot. There's a dot there. So A dot B plus C dot D. So that's A and into brackets B or C and D. So we see that they're not actually equal. So they're not actually equal. The circuits that you have here, the circuit I just drew, and the one on top, they're not the same thing. See, there are two different circuits. That's the circuit on top there, and the circuit below. They're not the same circuit. They are two different circuits. So we've been able to differentiate, or we've been able to prove that they're not equal. Those two expressions are not equal. This expression is not equal to the one on the right. The one on the left is not equal to the one. Now, what was the original expression actually? The original expression was like this. This is the original expression. The original expression was of this nature. Let me move this to the right a bit. Move this like this. The original expression did not have any brackets. Now, the original expression is equal to the one with brackets, because if there's no bracket there and you want to draw this, it has to be the one on the left, because and has precedence over all. So if there is no bracket there, if you don't put a bracket there, if there's no bracket in your expression, Boolean expression, you want to draw it out, it's better to always put brackets around the ones that have the AND gates to show that they have precedence. They take precedence. But if you get your bracketing wrong and you put it with the plus, with the OR gate first before the AND gate, you're going to have error, and they are not equal. So we've used the diagram to prove that they're not equal. We can as well also use truth table. So we can use the truth table to prove that they're not equal. We can use the truth table to prove that A dot B into brackets, then plus into brackets C dot D is not equal to A dot into brackets B plus C dot D. We want to use the truth table to prove that they are not equal. So let's draw the truth table. So in this truth table, there are 4 inputs, A, B, C, D, and 1 output. There are 4 inputs and 1 output. So the truth table is actually going to be longer. So this for the first time in this course, we're going to be drawing the truth table for 4 inputs. We've done the input for single input, single output. We've done for 2 inputs, single output. We've done the truth table for 3 inputs and 1 output. Now we are going to be doing for 4 inputs. So we start by the output. The outermost part will have 8. Okay, let's duplicate. The table has to be a lot larger. Let's reduce the row size, reduce the font size, reduce the row size again, and then create extra rows, insert. So it's going to have the outermost column will have 8 zeros, 8 zeros, 8 ones, 8 zeros and 8 ones. The next one will have 4 zeros, 4 ones, 4 zeros, 4 ones until you fill up the space. The next one, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones. Last one, 1 0 1 1 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1. So see that the outermost one, 8 zeros this time around, 8 zeros, 8 ones. The next one, 4 zeros, 4 ones, 2 zeros, 2 ones, and last one, 1 0 1 1. So for 4 inputs, it's slightly different. If it were 3 inputs, we would have started with 4 zeros, 4 ones. But since it's 4 inputs, we start with 8 zeros, 8 ones, and then followed by 4 zeros, 4 ones. So if you have 4 inputs, if your digital logic circuit has 4 inputs, this is how it has to look like. So you don't have to cram it. Just know that the outermost one will have 8 zeros and 8 ones. The next one with 4 zeros, 4 ones. The next one, 2 zeros, 2 ones. And the last one, which is D, is 1 0 1 1 alternated until you fill up the space. So there's no how you want to combine 4 inputs, 4 digital inputs, that it won't fall. What I want, that you won't get this combination. This is the permutation for or the total number of ways you can arrange 4 inputs A, B, C, and D. So let's get the digital equivalent, oh, sorry, not digital, decimal equivalent of A, B, C, D. Subscript. Okay, 10. So what is A, B, C, D in base 10? A, B, C, D in base 10. No, that didn't come out well. Ohm, font, subscripts. Okay, 10. Okay, now in base 10, 0, 0, 0, 0, 4 zeros in base 10. Let's bring out a calculator. Search calculator. Bring out a calculator. 4 zeros. Okay, 4 zeros. Binary. You click on binary. So A, B, C, D. 4 zeros binary. In decimal is still 0. Let's shift the calculator here. So 0001 in binary is 0001. In decimal is still 1. 1. Next one is 00010. 0010 binary. In decimal it is 2. In decimal it is 2. Next one is 0011. It's 3, 4, 5, 6. We've done all this one before. 7. We stopped at 7 before. 7. See that the last one, A, is 0 because it didn't exist before in 3 inputs. Now that's 4 inputs. We can now continue for 4 inputs. So that's 1, 0, 0, 0. That is 8. In binary it is 1, 0, 0, 0. In decimal base 10 is 8. So that is, no, sorry, delete, down, 8. The next one, 1001. A, B, C, D. 100 A, 1, binary 1001. In base 10 or decimal it is 9. 9. The next one is 1010. 10. It will be 11, 12. It just follow that trend. 13. For 14, let's confirm that 14 is right. 1110. Decimal is 14. So that is 14. And the last but not the least, all ones, 15 decimal. So with this arrangement, actually, you are actually feeding as input decimal number 0 to 15 to your digital logic circuit or combinational logic circuit. So if A, B, C, D, you combine A, B, C, D together, you convert it to base 10, you have 0, 1, 2, 3, 4, 5, up to 15. So let's insert a new column to the right, and that would be our E, output E. So output E for the first one, for the first column is A dot B plus C to bracket C dot D. A dot B plus C dot I hope you can see it. It's quite small. Let's extend. A dot B plus C dot D. A dot B plus C dot D. Let's adjust the circuit a bit. Yeah. Let's adjust this. Adjust. Okay. So we see here that the circuit on top, this first circuit on top, A dot B plus C dot D, we want to get the truth table equivalent of the first circuit. There are two circuits here. We want to get, so it's 0, 0, 0, 0, 1. Let's see, 0, 0, 0, 1. Let's simulate 1. E is 0 at this point. Now when we have 0, 0, 0, 0, 0, 1, 1. When C and D, so when C alone is 1, 0. When C and D are both 1, output E is 1. When A and B are 0 and C and D are 1, the output E is 1. When C and D are 1, one side of the OR gate is 0, and the other side is 1, and the output is 1. So this should be 1. Then 0, 1, 0, 0. So this is 0, 0 0, click 0 0 0 1. So the output E is 0. The next one 0 1 0 1, 0 1 0 1. That is 5 in decimal. Click here 0 1 0 1. The output is still 0. So if you feed decimal 5 to this circuit, you have 0 at the output. 0 1 1 0. A is 0, B and C are 1. Click 1. So the output is still 0. The next one 0 1 1 1. 0 1 1 1. You see that one side is 0, the other side is 1. The output E is 1. The next one is 1 0 0 0. 0 0 0 0. Here 1 at the top, 1. So the output E is still 0. The output E is 0. The next one is 1 0 0 1. 1 0 0 1. 1 0 0 1. At the input, the output is still 1. Sorry, 0. The next is 1 0 1 0. So A is 1, B is 0, C is 1, D is 0. 1 0 1 0. The output is 0. E 0. Click 0. The next one is 1 0 1 1. A is 1, B is 0, C and D are both 1. So the output here is 1. The output 1. Then 1 1 0 0. 1 1 0 0. Only A and B are 1. The output is still 1. The output here is 1. The next one is 1 1 0 1. 1 1 0 1. The output is still 1. Next one is 1 1 1 0. 1 1 1 0. The output is still 1. Then all ones. One of the inputs are all ones. The output is 1. So we've been able to generate the truth table for the first circuit. That's A dot B plus C dot D. When you feed decimal 0 up until decimal 10 to this circuit, you only have 1 when you feed 7. If you feed 2, you have 0. If you feed decimal 3, you have 1. If you feed decimal 3, you have 1. You feed decimal 4, you have 0. You feed decimal 5, you have 0. Decimal 6, you have 0. If you feed decimal 7 to this circuit, you have 1. So you see here that this circuit only has an output of 1 when you feed some particular types of input to it. For example, if you feed 4 5 to it, you get 0. You feed decimal 6, you get 0. You feed decimal 7, you get 1. Decimal 8, you get 0. Decimal 9, you get 0. Decimal 10, you get 0. Decimal 11, you get 1. 12, you get 1. 13, you get 1. 14, you get 1. That is if your input is a 4 input. If it's a 4 input, use 4 inputs digital circuit of this nature. This is the truth table. So this truth table, it describes the behavior of this circuit A dot B plus into bracket C dot D. So let's insert another column to the right. Now we want to differentiate. We want to prove that these two circuits are not equal using the truth table. We have used the circuit diagram to prove they are not equal. One circuit has 2 AND gates and 1 OR gate. The other one has 1 OR gate and 1 3 inputs AND gate. So we've used the circuit diagram to prove that they are different. Now we want to use truth table. So the next column, or the last column of this truth table is A dot into bracket B plus C dot D. So is the second guy we want to prove. We want to prove that the values, if they're actually different, then their values should be different. The values of E, their output should be different if we run the same kind of input. If we run the same set of inputs through the second circuit, the output should be different from or different to the initial or the first circuit. The second circuit should produce a different output to the same set of inputs. So let's prove that by running a simulation. 0. Now, when all the inputs are 0, the output is 0. We've seen that. When only D is 1, the output is still 0. The next one is when only C is 1. When only C is 1, the output is still 0. When C and D are 1, C and D are 1, the output is still 0. When only B is 1, 0 1 0 0 sorry 0 1 0 0, the output is still 0. 0 1 0 1 0 1 0 1, the output is still 0. Then 0 1 1 0, that's A B C D. 0 1 1 0 0 1 1 0, that's the output is still 0. The next is 0 1 1 1 A B C D. 0 1 1 1, that's the output is still 0. Then 1 0 0 0 1 0 0 0, the output is still 0. The output is still 0. The next is 1 0 0 1, the output is still 0. Next 1 0 1 0, the output is still 0. 1 0 1 0, the output is still 0. See here that both sides of the AND gate are turned to be 1 there, and the D is 0. Until that AND gate has 1 on all sides, it will always be 0. That's 0 there. And the next one is 1 0 1 1. 1 0 1 1. For the first time we have 1 here. That is because the AND gate that last AND gate has 1s on all its inputs, and the output becomes 1 for the first time. 1. The next one is 1 1 0 0. 1 1 0 0. A is 1, B is 1, C 0, D 0. So 1 1 0 0, 1 1 0 0, the output is 0. And next we have 1 1 0 1. 1 1 0 1, the output is 1. 1 1 0 1, the output is 1. 1 1 0 1, the output is 1. Next one is 1 1 1 0. 1 1 1 0. D 0 1 1. A B C are 1 and only D 0. The output is 0. And then A B C D are all 1s, and the output becomes 1. So we see here that for the second circuit, the output is 0 almost throughout, until just apart from 3 values, it's basically 0 all through. So we see here that by using the truth table, we are able to prove that these two circuits or these two Boolean expressions are not equal. This expression is not equal to this second expression. We use the truth table to prove it, so that their values are different. 0 0 1 0 0 0 1 0 0 0 1 0 0 0 1 1 1 1 1. So if you feed this decimal input 0 to 15 to this circuit, you feed 0 1 2 3 to this. When you add 3, if you feed 3 to the first circuit, it gives you 1. The second circuit gives you 0. You feed 7 to the first circuit, it gives you 1. The second circuit gives you 0. You feed 11, both of them gives you 1. If you feed 11, the decimal 11. You feed decimal 12, only the first circuit gives you 1 and the second circuit gives you 0. You feed decimal 13, so and like that. So we see here that we can either use the circuit diagram to differentiate the two, to prove that the two logic expressions, Boolean expressions, are not equal, or you use truth table. So we use two methods to prove that these two Boolean expressions are not equal. So we prove that they're not equal, 1 using the diagram and 2 using the truth table. So that will be the end of today's video lecture series, or today's video lecture module 2. So thank you for keeping tuned with me. I hope you are able to grasp all the concepts that we examined today. So work on the assignments, and I'll see you in module 3. Thank you.